Guys, let's begin our meditation. So it's good to meditate on the third eye and the heart. Both of them will help in the marriage of knowledge and understanding. So we're seeking to make mathematics the means by which we can become more conscious, the spiritual path of mathematics. We have to recognize the aspect of conditioning that prevents mastery. So multiplication is something that's usually memorized. We study multiplication as the means by which we can traditionally do practical things, right? So you're like, okay, well, how much money do I owe the restaurant? Things like that. But as a spiritual path, we seek to try to begin anew every time and prevent ourselves from relying on conditioning. Now, this is quite challenging because if I ask you what's 8 times 8, you're almost immediately going to see 64 in your mind, unless you somehow didn't know that. So the question is, how can we urge ourselves to be forced to not simply perform a multiplication based on memory, but develop the faculties of multiplication? This is a difference between memory and faculty. So the faculty of 8 times 8 is 64 is to recognize that 8 sets of 8 is 6 sets of 10 and 4 more. How could you see that? Now, it's very rare for anybody to see that at all, right? How would you even do that? Most people would think, I don't know, how would I do that? And so we haven't developed or emphasized developing the faculty of multiplication. Now, there's a faculty of calculus is faculties of different parts of calculus, different parts of fourth dimensional geometry, of different parts of spherical coordinates. There's faculties there. So instead of becoming a machine, a robot, and being able to perform mechanical tasks, we seek to be able to see, behold mathematics, see it. The faculty is the seeing in mathematics. So I just did an animation with a tree fractal. You guys might have seen that. Did you see it, Robert?
No, it popped up and it was one of those things where it went right to the bottom and I didn't get to see it
Oh, okay. You have
of
to.
Instagram feed. I got to check it out though. I was excited to see that you posted one.
Yeah, so in that one I had to use spherical coordinates. So I spent a lot of time really connecting with what are spherical coordinates, experiencing spherical coordinates. You can just memorize them. You can just apply the equations, which I do to a degree sometimes. But to do only that is not developing the faculty of comprehending spherical coordinates. And if you don't have the faculty, you can't meet a novel challenge fully. So say one day you're working at Tesla, and they're asking you to do something, or you need to do something, you need to create some machine, some part. Well, you have to think creatively. So mathematics moves into the dimension of creativity when we emphasize faculty. Now, if we don't do this with basic math, how could we do this with advanced math? I mean, you can, but I think it's an easier thing to try to do it with basic mathematics. So if I were to say, okay, what's 8 plus 8? Well, 16. But what does that really mean? It means 1, 10, and 6. Why? Because one of the 8s gave 2 to the other 8 and had 6 left over. 8 plus 8, we have 8 and 8. One of the 8s breaks off 2 of himself, gives it to the other 8, so it makes a complete set. We call that the 1 in 16. And then we have 6 left over. So if we were doing it in base 12, the 8 would have to give the other 8 4, and we'd only have 4 left over. Right? What about in base 16, also known as hexadecimal? Hex meaning 6, dec meaning 10, hexadecimal 610 means base 16. So in base 16, we would have 8 and 8, and we'd actually get 16, which would be one set. So today's course is on transcending base systems. We want to distill arithmetic of human artifact and try to see more directly what these things are. What is 8 plus 8 in base anything? Like what? And you could do smaller bases like base 4. What's 8 plus 8? Well, that would be, wait, that's 2 4s. Okay, that's 4 4s. Okay, that's 1 4 4. One set of 4 sets of 4, which is actually 1 0 0. So 8 plus 8 in base 4 would be represented as 1 0 0, which is the same thing as 2 0 plus 2 0 equals 1 0 0. Okay, so I'm just giving you a few examples. I'm actually not 100% sure how obvious this is, or if it's completely not obvious and I'm just talking way too fast. So I would encourage anybody to say anything about it. I'd like to really help you guys be able to basically what I called it binumeral or trinumeral, meaning that you become familiar, not memorized, but familiar through practicing the faculties in at least 3 bases, primarily familiar. I think base 10, base 12, and base 2 are a nice group of 3 bases. Base 16 is nice to know. Base 8 is nice to know. Base 5 is nice to know. Base 3 is nice to know. I mean, it's nice to be able to do all of them, but I think binary, dodecimal, and decimal are very good. Hexadecimal is very common in computer programming, so maybe that one's good too. But I don't think it's as natural as 12. 12 is a very natural set size. And it seems to come up a lot in the world. 12. 12 dozen. How many disciples did Jesus have? 12, right? Like there's always 12. There's a witch's circle has 1 and 12, 13. There's kind of 12 lines on the longitude lines on the Earth, all at 30-degree marks. And every 30 degrees and there's 12 of them. And the reason for this is 12 is a multiple 4 and a multiple 3, which makes it a very superior base system. In fact, if I was designing human thought from scratch and we could go back a million years or something, I might suggest 12 instead of 10. But 10 is also a good base system. So it has its own benefits. In base 10, 1/3 is represented with repeating decimal, 0.3 repeating. But in base 12, 1/3 is represented as just 0.4. So we're going to go into all these things in a second. In base 10, 1/4 is requires 2 decimal places. In base 12, it still requires only 1, 0.3. Now, 1/3 and 1/4 are very important. In base 12, 0.6 is 1/2. So why is 0.6 1/2 in base 12? So 0.5 is 1/2 in base 10, because 0.5 means 5 out of 10 as a fraction. In base 12, 0.6 means 6 out of, well, it has to be out of 12. So we want to develop this faculty. So if you're doing your 15 minutes a day of mathematics, you can practice basic arithmetic in different bases. And you have to get the gist of how to figure it out on your own. Then you can go to the internet and say, wait, am I right about this? You know, is 1/5 in base 12 this number, which is actually kind of difficult to calculate? And then you find it and you're like, yes, I got it. Or maybe you didn't get it. So there's ways to check, but you have to understand the basics of it. So we can go over that today, and then you can practice it and explore it. But the whole idea is to develop a mind that is not resting on conditioning. So we want to be very active mind that comprehends mathematics, comprehends multiplication, and is present enough to do it each time. So if I said do 8 times 8, and you could actually do it, like I just did it. I actually did 8 times 8 equals 64. Which we went over in the previous class. Okay, what about 8 times 9? Okay, just did it again. That's 72. I could see it. So the goal is to see it. Now, it is more work, but in the long run, it's not more work, because what you're doing is you're developing a more well-structured mind. What does more work mean? If we're valuing the efficiency of our work based on the results of our actions, then perhaps initially, but maybe not in the long run, or maybe also in the long run, we won't achieve as good of results in terms of output. But if we're prioritizing a well-structured mind, which one do you think is better? If you can actually multiply and do it in any base, or if you just memorize it, what develops your mind more to be a better, well-structured mind? And then you ask yourself, well, what is mathematics? What's it for? Well, for a pure mathematics lover, we like mathematics for mathematics. Now, it can be a utility, of course. It can be applied. So if it's being applied, you might say, well, just pick a base system and use it, right? Because maybe you don't want to change it, but then maybe you come up with some engineering situation like a computer where you have to use base 2. You save a lot of money by making a computer a base 2 computer. And the reason for that is a transistor is a very basic module of hardware because it's either on or off. If we had to make a transistor say on, off, 10 different spots, it would be a very complex device. So we can etch these things at the atomic level, just a couple nanometers now, and create them because they're very simple. But then we have to do everything in binary. So who's the genius that thought that up? Well, somebody had a well-structured mind. A bunch of people had to have a well-structured mind, right? So I would argue that in engineering, it's beneficial, especially in the long run. Maybe not if you're just just doing monotonous tasks, if that's what you want your life to be. You're like, you just crunch the numbers for the company. They're using your brain power. And with the age of AI, with the age of computers, with the age of calculators, these things have become somewhat obsolete. When last did you really need to carry a one, borrow, do all those things? I almost never do that. I mean, I probably because I do math differently. But even then, you don't really need to do those things unless you're doing them for a spiritual reason. To see it, to experience it, to experience 1/3 in binary. I love 1/3 in binary. It's beautiful. Because binary is base 2 and 1/3. I like how Ayush is like, but what is it? Wonderful. We should do 1/3 in binary. It's a fun one. I can show you geometrically. Okay, so lots of things to talk about. I'd love to answer any questions. I really want this to be something very valuable to you guys. If I'm not really loving you guys by providing value and making your life better, then I'm not sure what I'm doing. I want to make sure that this is valuable for you. So there's a little bit of a black box situation. I have no idea how any of this is landing for everybody. If you're having more happiness, more joy. So Robert's about to say something, I think. Yeah.
I don't know the other bases very well, so this is all good to like hear you kind of explain it better. I've never really dove into this very well and thinking about 1/3 and binary. I wouldn't know where to start really, honestly.
Yeah. It's okay, cool. Ayush, do you want to say something?
Yeah, same with me. Like I've never counted in binary or in hexadecimal or like this, but yeah, I'm really excited to learn this and restructure my mind with 50 patterns. Like just
We got to get you a better microphone, Ayush. You can get a better microphone for $5. Go
yeah,
buy
sure, sure, sure.
go
I
buy
will.
the cheapest headphones you can find that are, I'm not sure, maybe that's water damage or something. Or maybe it's just, yeah. It's very hard to understand what you're saying, and it kind of hurts the ears when you talk because it's because
Oh, okay.
the microphone's really, really not good. So, but what can you say one more time?
Yeah, so I was seeing that it's good to know about different numeric systems like by uh, binary and hexadecimal. I was searching about the utility in current times. If we ignore the computer science and if we just count like this, so how like in uh, because if
I'm really having trouble hearing you. It's actually cutting out. Um,
the utility in the real life or the day-to-day life like doesn't seem much to me. So I was just thinking about that.
the utility of it in day-to-day life. Well,
Yeah, yeah.
what's the utility of, this is another thing about math is knowing these mathematical structures immediately changes your whole world. For example, if you went to Disneyland, Disneyland, you came back to India, you came back to Wisconsin, you would see the world differently. because you're looking through your wisdom, your life experience. If you knew art history very in depth, you would look at cars differently. You'd see the art in cars, the evolution of history in the way cars are designed. You'd see everything differently, right? So we have to really value the human achievements, all of them, and recognize the ways that they augment and develop our subjective experience. They all do. I recommend studying poetry. I recommend studying everything you can study. Because there's a dimension, I mean, especially the great works, you know, maybe know a little bit about the great achievements and contributions some individuals have made to society over the last 5,000 years. Maybe let's call it 3,000. So mathematics, my point is that mathematics is very relevant. If you know binary 1/3, you know, this tree fractal, I'm seeing tree fractals everywhere now. I did the tree fractal. I'm actually astonished at how much a tree is very much like a tree fractal. They're very much like tree fractals, and they almost are the same as a tree fractal. So so I'm experiencing these things. So what you focus on, you become. And so also when you focus on something very pure, like 1/3 and binary, it's so truth-based. It's pure truth, and it's pure perfection. There's no room for imperfection. It is what it is. It has there's no chip in the side of it. It's not perfectly polished. You know, in the movie Tron, then the new one, you get the sense that the floor is like perfect glass from like acres, right? Of perfect glass floor. And so mathematics has the quality of this perfection. So that enriches your life, and you may organize your home differently. You may organize your Excel spreadsheets for your work differently. You may do all kinds of things. And most importantly, you will develop a well-structured mind so that you can surrender and become absorbed in consciousness more deeply. So that's the spiritual benefit. And you're just a more powerful individual. Whatever you put your mind to, it's more powerful, so that you can really set yourself up in the world to practice your spiritual path more effectively. So those are some of the reasons. So okay, let's just dive in to have some fun here. This is a different whiteboard to the one I'm used to using. Okay, I'll use this one. So binary. So first of all, 8 times 8. Can we see this? If 10 by 10 is 100. How can we see 8 times 8 in here? Well, we could take 2 10s off the top, 2 10s off the side, and there would be our 8 by 8 in this section. So in a way, we subtracted 40. So instead of 10 10s, we have 6 10s. But we used the corner twice. So we have to add 4 back. Let's make sure everybody gets it. So we have, instead of 10 10s, we have 6 10s, because we took 2 off the top and 2 off the side, but we took the corner twice. So we have to count for that and add 4 back, which I hope makes sense. So we can see.
I can't see the whiteboard.
You can't
like it said like, oh, retry to load this whiteboard or something, and now it says it's like at an error message or something. Ayush, can you see it?
Yeah, I can see the whiteboard.
Oh, like it'll pop up right now and it says connection error, unable to load this whiteboard.
Hmm.
Huh. I can see it now.
You can see it now?
Huh.
Okay. I just
Yeah.
okay. So take
Yeah.
a look at that. Does it make sense, Robert?
Yeah, that's what I was envisioning earlier when you said 8 times 8, in your head, but it's still like it seems slower, but I could see where like when you start to do that regularly, it would be incredible to just be able to visualize it that way.
Well, what's 18 times 18? Right?
Yeah, right. I don't know. So I guess I would envision try to do the 20 by 20 and
Okay.
then minus the
Let-
two
Let's
20s.
let's see if you can do it before I draw it.
Okay, so I'm gonna draw a sketch in my book.
So 20 times 20 looks like this. Each of those is 100. Taking 18 off. 2 layers off each side. So what have I taken off? I had 400s and I took off 20, 20, 20, 20. So I took off 80.
80.
I've got 320 now. And then you add 4 left. Add 4 more. So 18 squared is 324. What about 28 squared? So if I want to do 28 squared, same thing. In this case, we get 9 sections here. We have 900. We're going to take 2 30s off the top and 2 30s off the side. So we're taking 120 off. So 900 minus 100 is 800. 800 minus 20 is 784. 784. What about 29 times 28 though? So if we do 29 times 28, it's the same thing. Very similar. We've got 900s again. This time we're taking 1 off the top to make it 29 tall and 2 off the sides. So we've taken off 90. So we have 810, but then we have to add 2 back. So we have 812. 29 times 28. So let's just do a little practice. What is 18 times 19? Hmm.
342.
Very good. Yeah. What is 17 times 19? And don't rush. Do you have an idea, Robert?
323.
Yeah.
Oh, nice.
Okay. So now let's play around in some hexadecimal because you're doing this differently. So you can do hexadecimal. So in hexadecimal, what is F times F? Now F means 15. So F times F, where F is 15. Why is F 15? because A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So F squared is 15 squared. And if you were to think of that, here's our 16 by 16. Take one off the top, take one off the side, you have 15 by 15. So now you don't have 16 16s, you have 14 16s and one more. Ayush, what do you think? Do you got it?
No, you are doing for base 16 and then you said
Mhm.
I got till F square. So F square is 16 by 16.
F squared is 15 by 15. How
Okay.
many 60? Yeah, because this is 15, right? So I'm
Okay.
kind of saying like 15 squared. What's 15 squared in base 16? But you have to use the letters, or you don't have to use the letters actually. The question is how many 16s is it and how many more? So 15 15s is how many 16s and how many more? So
Yeah, got it.
we took a 16 off the top and off the side. So how many 16s do we have in that case, not including the corner, Robert? Well, we took 2 away, right?
Do we have 1 or 10? Would that be called? Or I don't know.
Well, if we have 16 16s and we take 1 16 away, how many 16s do we have?
15.
Okay, if we take 2 16s away, how many 16s do we have? Don't overthink it. I'm asking this very basically.
Wait, repeat the question, please.
If you have 16 16s and you take 2 away, how many do you have?
14.
14. So that's what we did here. We had 16 16s. We took 2 away, one here and one here. Took them away. So now we have 14 16s, but we have to add the corner back. So the answer,
Oh, I can see where this is beneficial. Looking at it this way now. Yeah.
so we get E1, where E is 14 16s and 1. And you'll find if you multiply 15 squared is 225, 14 times 16 is 224, plus 1 is 225. So you can actually check it that way. Now, do you see how easy that was for me to think about that? And I didn't prep for this class, just so you know. Like this is just, I'm just thinking about it. Well, I was thinking, well, okay, we'll talk about that. Okay. So I'm saying that not to brag. I'm saying that to encourage you guys. You can do it. Think about how nicely, how nice your mind will be. Very clean, orderly. So this means 14 16s and one more. So Robert, let's focus you and me. Let's keep going. Ayush can watch us go through this, and Jacob can do whatever he's doing. Correct. So let's make sure you're getting it. Because if you're going to be teaching the kids base 16, can you imagine you're 12 years old and you're learning base 16? And there's no reason why you can't. I mean, it's not rocket science, right? But it will be a nice foundation for whatever you want to do. It's better than rocket science. It's math science. So Robert, I'm wondering, okay, so what about E times E? What's E squared? Now notice this was kind of like the 81 of base 10. 9 times 9 is 81. Take away 2 10s and add 1. Take away 2 16s and add 1. This is the 81 of base 16. So what is E squared? E squared.
E squared. So 14 squared base 16. So you'd be 16 sets of 16 and then minus 4 16s.
Okay, very good. So 16
So
minus.
how many 16s do we have then? Would you say like 12 and
You
then
have 12 16s.
remainder 4? Or how does that, like, how do you say that?
You're right. 12 16s and 4. 12 16s plus 4. But that's what this means. The 12 is represented by a C. Since it's in the tens place, which is now the 16s place, that means 12 16s and 4. There you go.
Okay, okay.
All right, let's do D squared.
So you'd be 10 with the remainder 9. So
Woo!
you'd call that, oh, 8, 9.
Yep. You see how-
Dang.
Now, okay, so awaken the genius in humanity. We're seeing it happen before us right now, right? There's a latent genius in us that has been stymied by superficial approaches to mathematics. Although, even when you read when I read mathematicians every now and then, when I have just glanced at some of the ways they did things like a long time ago, they didn't do it as visually as this. And I'm not sure why. I'm not sure why. I mean, maybe, I don't know. To me, this is a very important thing to be able to do. The fact that you just did D squared equals A9 and you didn't grab a pencil, or actually maybe you do have a pencil, but it looked like you did it almost instantaneously. This is the theory, the argument here is the hypothesis, which is not much of a hypothesis. I can assure you. I don't want to assure anybody, but let's not say I can assure you. I can assure you, but I feel very clear that if you start doing math this way, math will become easier. It will become more fun. You'll be more creative. It will expand more quickly. You'll be able to answer novel questions more effectively. You'll structure your mind more completely. And most of all, it'll just be more fun. I mean, this is pretty fun. I think it's fun, right? I mean, if we were like, what's 14 times 14? That would not be fun, right? But if you were just trying to do it, right, it would be boring because you already know you can get the answer. You just have to go through this long process, right? But the fun is in being able to awaken genius, to be able to see it, snap insight. Sometimes you see the answer before you even realize how you got there. You're like, oh, wait, was that it? You see the letters just pop out of your head. And that's really cool. So I'm saying that genius is a function of our approach to mathematics more than it is a function of some sort of innate capacity. It's also a function of energy work. If you clear your energy, you go into light, you experience Shakti, it really increases your intelligence enormously. Your emotional intelligence goes up and your intellectual and abstract intelligence goes up. And your wisdom goes up. Everything goes up. You know, how do prophets do mathematics? Probably pretty well if they put some effort into it. And you'll find that there's a sort of depth of intelligence that some spiritual people have if they choose to direct their attention that way, whatever they do. Like a Nikola Tesla had some spiritual faculties, and all of a sudden he creates a bunch of machines that nobody could even conceive of. First one to do it. It's really impressive. Very impressive. Okay, let's do another one. What is C squared? So C is 12. Wow, really?
Would it just be 9? Or how does that work?
9/16, right?
9/16, right? Well, I had 8 and then you like a whole 16 in the top corner, right? With the
Yeah.
4x4. So you'd call that a 1, basically,
Uh-huh. Or you'd call that
or that becomes a 1. Yeah.
another 16, right? So we basically
Another 16. Okay.
we have the 8/16s, and then the corner gives you another 16. And I don't have to see, I don't even like that I did that. But you know what that does. Gives you 9/16. So this, it's interesting. There's no counterpart in base 10 for this. In base 10, no perfect squares equal a multiple of 10 except for 10 squared. So c squared is a perfect square in base 16 that equals a multiple of 16. So excellent job, Robert. Okay. So pretty good. Now let's talk about binary for a moment before we run out of time. So what is 0.1? Well, depending on the base, that means 1 out of the base. So in base 10, that means 1/10. It's a fraction. 1 over the base. In base 16, that would mean 1/16. So then what does 0.01 mean? Well, that means 1/10 out of 1/10. It means 1 over the base squared. In base 16, that would be 1 out of 16 squared, which would actually be 1 out of 256, which is 16 squared. So if each time you add a 0, you take a fraction of that fraction. It's kind of like we're saying, well, what's 1/10 of this, right? Because we moved it over 1. So in binary, what is this, Robert?
I don't know. 1 over 1. So 1,
Well, binary is what base? In base 2.
2.
It's 2. So it wouldn't be 1 over 1. It would be 1 over the base. 1 over the base.
Oh, I see. Like the base. Yeah, that makes sense. Yeah.
So what would it be?
Well, base 2, so 1 over 2.
That's 1/2. This is 1/2 in binary. Let's wrap our minds around that for a second. Now, notice the pedagogy I'm using here. I'm starting with the most essential. Very important to do this when you're teaching kids and yourself too, especially yourself. You're sitting, nobody's gonna help you out. You're sitting by yourself trying to figure out some math. Sure, you can use ChatGPT, but you're still kind of, ChatGPT doesn't always just give you the answer, right? So you're trying to figure something out. How do you do it? Start with the basic, distill it to the most basic building block you possibly can. And then what matters is that you move your mind state into that. You should feel immersed in the realm of that contemplation. So it's not enough to just say it. You sit and be with it. Okay, point 1. 1/2. Okay. It means 1 out of 2. Or 1 out of b, 1 out of n. It's 1/2. It's a fraction. It's less than 1. Okay. Then you can stop your mind. Be with that. You see, so this is the approach. This is the pedagogy. The pedagogy is we want to take incremental steps. Now, once you get this, then only then will I add another layer. 15 years ago, I called this progressive dynamic response. Actually, I should probably still call this. This was 15 years ago when I was tutoring and I had my first tutoring agency. And the whole basis on it was a little more mechanically focused though. But I think this is still valuable. I hadn't brought the spirituality into it to the same degree. progressive dynamic response. It means you progress, and when you work in a tutoring situation, you're dynamically adapting, and then you respond based on the student. So the student says they get it or they don't. If they don't, it's kind of an if then. I could code this too. It's like if they get it, if they don't. If they get it, you can take it to the next level. Maybe they need to get it 5 times first in 5 different ways. And then if they don't, you keep giving them the questions and really maybe even going backwards into more basic building blocks. So if this is 0.1, then, I mean, 1/2, then what's this?
One over 4.
Yeah, good job, Karan. I was going to ask you, Karan, if you wanted to say. 1/2 of 1/2. Okay. So what if I put 5 zeros in a 1? What's that?
Be 16. 2 to the 5th.
So close. 5 zeros.
Or
Yeah.
32 or 1 over 32 then?
Well, you're so close. You're saying 5. But remember here, how many zeros were there? There were 0 zeros.
0 zeros.
So I have to think of it in terms of places. So it's actually 6 places. So it's 1 over 2 to the 6. Right? Well, look, this was 1 0, but it's 2 squared. Right? So we really want to know how many places is the 1 after the decimal point. Okay. Robert, does that make sense?
Yes, got it.
Cool. Okay. So then now watch this, guys. If this represents 1/2, this represents 1/2 of 1/2. This represents 1/2 of 1/2 of 1/2. This, the next one, the next one, the next one, and so on forever, right? So here we can see that 1/2 plus 1/4 plus 1/8 plus 1/16 forever actually adds up to 1 because it fills in the whole square, which originally was equal to 1. So what is 0.1 repeating in binary? Well, that's 1/2 plus 1/2 of 1/2 plus a 1/8, 16th, so on. It actually equals 1. But we've just seen it geometrically here. Do you guys get that? Do you see that equals 1? It's a funny thing because in base 10, we can actually say 0.9 repeating equals 1 as well. 9/10 plus 9/100 plus 9,000 plus 9/10,000. If you do that forever in the limit that, which is what this is, it's a limit, that actually equals 1 as well. Isn't that interesting? And in some higher mathematics, they actually use that. It's actually used in some grad school math. 0.9 repeating equals 1. Okay, so did you get the 0.1 repeating?
Yes, I got that 0.1 repeating, but I could not relate 0.9 in decimal to 0.1 in
I didn't.
Because there is only 1 digit in the binary and there are 9 digits, 10 digits in the decimal.
Yeah, let's do that another time. It'll be related to what I'm about to show you here. So what is this? This is 1 out of 4. Right? if this whole thing is 1, then the first part is 1 out of 4, 1/4. Do you think I want to put stuff like this on Instagram? I wonder if people will like it. What do you guys think? I think it would be fun.
Yes, if you do a different coloring, then it will be great.
Different
I
color.
guess. Yes.
I'm not. You mean not blue and white?
Yes, maybe a bit more colorful.
Well, I would do it with code and I would make it black with rainbow. So so I would do it my way. But I mean, but this topic is what I mean. Okay, so this is 1/4. What is this? Robert, we're losing you, man. We got a couple minutes. Karan, what's that?
Is it 1/4 of 1/4?
Exactly. So that's 1/16. And if I do this again, this is 1/4 of 1/4 of 1/4. And if I do it again, and 1/4. Now, so what's 1/4 plus 1/4 squared plus 1/4 cubed plus 1/4 to the 4th to infinity? If I keep doing this forever, you say, well, Adam, I don't know. I can't. But when you're like, wait a second, for every blue one, there's 2 red ones. So what fraction did I fill in when I shaded the blues? One-third. So 1/4 plus a 16th plus a 64th and so on equals 1/3. So what is a 4th in binary? A 4th in binary is this. What's a 16th in binary? This. Right, because it's 2 more decimal places. So it makes it 4 less. What's a 64th? This. What's a 256? This. What's a 1024th? This. What's a 4096? This. Wait a second. I'm seeing a pattern here. 0.01 repeating equals 1/3 in binary. I'll take my bow. The bow is in order. Let me just make sure you guys get it too, though. And this is represented by this thing I showed you here. 1/4, 1/16, right? Keep taking one of each. 1/64. So 0.01 repeating is 1/3. Robert, let's hear it. We got to wrap up, so I want to make sure this makes some sense to some of you guys. All of you guys, hopefully. Robert, can you hear me? Oh, froze again. Okay, Karan, do you understand?
I understood the pictorial view, but not these letters.
Okay. Do you understand that this is 1/4 and this is a 1/4 of a 1/4 and a 1/4 of a, you understand that?
No.
Okay, so every time we move 2 decimal places, so this is 1/4. This is 4 times smaller. Why? Because we move 2 more decimal places over. And each decimal place we move 2 times smaller. Karan?
Understood. Now the 1/4 was 0.01 and we are just repeating it.
Well, if we do it again, we've got more zeros and then a 1 further down. And when you add these together, this is effectively adding 0.01 plus 0.0001 plus 5 zeros and a 1, right? Plus 7 zeros and a 1. We're adding all of those parts. So this is the sum of all the force. In fact, you could write that as the sum of 1 over 4 to the power of n, where n equals 1 to infinity. So this equals 1/3. And this can be represented by adding this to the one with 2 more zeros, to the one with 2 more zeros, to the one with 2 more zeros. And it can be seen visually using this diagram that I did here. Robert, what do you think?
I think I have homework because I kind of I lost connection during the pinnacle of this, and I'm kind of catching the tail end. But I definitely am seeing what you're saying, and I saw like the 1/3 represented, like Fibonacci spiral going in there, you know.
Yep.
And I guess it was cool to see it with the 1/3. I don't know. It's if I have a full grasp on it, but it definitely makes sense.
Well, let me just ask you a couple of questions. Does a fourth plus a fourth plus another fourth of that, does that make sense that that's 1/3?
Oh, I see. Okay, so originally it's 1/4, not 1/3, where there's one red one, and then you cut it again.
Well, this is
Okay. So
this is 1, and so one of these is 1/4 for sure.
yes. Okay, I get it now. I didn't see the part where it was 1/4, and then all of a
Okay.
sudden, like my thing connected again, and only half the writing was on the screen
Oh,
because
okay.
the whiteboard was weird again. So sorry, my connection's bad.
That's okay. Let's just do it now really quickly. So if I shade in one of these each time, then you can see that I've shaded 1/3 of the thing in. It has to go to infinity though, right? You have to keep doing smaller and smaller rectangles. And eventually you shade in 1/3. So then we're seeing geometrically this. We're recognizing in binary that that's the same as this.
Okay, that's what I was trying to piece together, is how to put it back into, or where the binary would come in.
So this is 1/4. If you put 2 more zeros, 3 zeros and a 1, that would be 1/8. I mean 1/16.
Yep. Okay. Yeah, now I see it. If you sum those together and had all the zeros and a 1, all the zeros and a 1, and
Yep.
that's where that.
Every
Okay. Yep.
every other zero. In fact, in base 4, if you put all ones, that means 1/4, 1/16. You don't need the zeros in base 4, right? Because that's just, each of those is 1/4 as much. That will equal 1/3 as well. You can think about that. I mean, maybe you guys get that instantly, but the whole idea is we have to do 0, 1, 0, 1 because we have to do a half of a half. But in base 4, you don't have to do a half of a half. You just do a fourth each time anyway. And so 0.1 repeating in base 4 is 1/3. All right. Cool class. I hope, did you guys like this? Was this valuable to you, or is it just my thing? Okay. Ayush, did you like it?
Well, I couldn't understand it properly, but I do got it when you did square and half it, then again half, then again half, then again half, then again half, and then that the whole sum is 1. So yeah, I could visualize that. So
Wonderful. Okay. And how about you, Jacob?
Yeah. I think this is something that will be valuable to show your Instagram community.
Nice. Thank you. Yeah. Even just this example, see if I can teach it in 90 seconds.
Yeah. No, showing it pictorially like that, it's just a whole new way to visualize math happen.
What is 1/3 in binary? That could be the. This is 1/3 in binary. All right, let's meditate. Because we're trying to stick to the hour. Enjoy 1/3. Become 1/3 binary. Namaste, everybody. Thank you so much. Nice to see you. Hey. Spiritual math class. Yeah. I'll see you guys later. We're doing Zen tomorrow. I'm excited for Zen tomorrow. So I'll see you for the Zen principles. Namaste.